Hi, this is Vince again from Bryn Mawr College, and this is the do-it-yourself problem for energy conservation. So in this problem, we have a spring that launches a ball into the air at some angle, and we're given a few parameters, and we are asked to calculate the speed of the ball at its maximum height. So if we're going to solve this using energy conservation, the first step should be to write down an energy conservation equation. So why don't you go ahead and pause the video and figure out which terms to include in your energy conservation equation, and we will compare results when you unpause the video. Alright, welcome back. Let's compare our results here. So this is the form of the conservation of energy equation that I have. On the left I've got my initial state, on the right I've got my final state, and in both cases I've included terms for the kinetic energy, the spring potential energy, and also the gravitational potential energy. So your equation might look a little bit different than mine, and that's okay. You might have taken a few steps beyond what I've done here and simplified things a little bit. But at this point, I'd like to invite everyone to pause the video and we'll all catch up to the same point. So what I want you to do now is, without plugging in any specific forms of any of these energy terms, I want you to use the physical situation that we have here and manipulate this conservation of energy equation, simplify it a little bit, and get to a point where the conservation of energy equation is really showing the energy transfers that are occurring in this physical situation. So go ahead and pause the video now, and we'll compare when you unpause. Alright, welcome back. Let's compare our results once again here. So the first thing I did was I decided that my initial state would be when the spring is compressed before the ball is launched, and my final state would be after the launch when the ball reaches its maximal height. With these initial and final states, we could say that the initial kinetic energy is 0, because the ball is not moving, and the final spring potential energy is 0, because the spring is back to its equilibrium length. So then if we take this equation and subtract the initial gravitational potential energy from both sides, we could write it as the initial spring potential energy is equal to the final kinetic energy plus the change in gravitational potential energy. So looking at the physical situation, we start with stored energy in the spring, and then the spring transfers that energy to the ball, and the ball gains both kinetic and potential energy. So that's the energy transfer that we're seeing here in this problem. So at this point, why don't you pause the video and just plug in the specific equations for these three different energy terms, and we will meet back when you unpause the video. Alright, we're back again. So this is the result you should have gotten for plugging in the equations for the different energy terms. So at this point, we've got an equation with a few different variables, and we want to solve for one variable, v sub f. So now why don't you go ahead and pause the video, and without plugging in any numbers yet, let's just continue to work with variables. Take this equation and manipulate it to solve for v sub f, and we'll compare results when you get back. Alright, welcome back. So why don't we go through this step by step. I'll show you the steps that I took to solve this. So from the equation we have here, the first thing I did was to subtract mg delta h from both sides, and that allows us to get rid of the mg delta h on the side with the v sub f squared, so now the term with v sub f squared in it is the only term on its side of the equation. But now we've got to get rid of the factor in front of v sub f squared, so we could do that by multiplying by 2 and dividing by m. If we do that to both sides, we get this result. And then we just have to take the square root of both sides, and we've solved for v sub f. So you might have taken different steps than I did. For instance, you might have gotten rid of the factor in front of v sub f squared first, but you should have gotten down to the point where you have the same expression as I do for v sub f. So finally, just to wrap the problem up, we need to plug in numbers for the variables on the right-hand side to get a numerical result for the speed of the ball at its maximum height. So why don't you pause the video, and when you get back, we'll compare results for our numerical answer. All right, welcome back. So when you plug in numbers, these are the values you should be using. Just make sure that you're using SI units, so mass in kilograms and distance in meters. I've converted some of the values before plugging into this formula. So when you plug that into a calculator, you should get that the speed of the ball at its maximum height is 5.5 meters per second. All right, thanks for listening to this do-it-yourself problem, and good luck with your future physics endeavors.